Vanakkam. Welcome to this video on biomechanics. We have been looking at some practical examples, practical applications, measuring body segment kinematics using various methods. We looked at rotation matrices, we looked at Euler angles, and we will continue our discussion of angle axis representation and quaternions in this video. So, in this video we will discuss axis angle representations, quaternions, how complex numbers and rotations are represented, and how to find relative orientation using quaternions. So, every rotation in 3D essentially implies rotation about an angle or rotation of or by an angle about an axis. Yesterday I gave the example of where this body, let us assume that there are three principal axes under discussion, for example that axis and that axis. These are the three principal axes. Now, let us say this body is undergoing that rotation, right. The axis about which the rotation is happening will have components in this axis and the vertical axis, and the rotation earlier it was vertical, now it is horizontal. The rotation is about 90 degrees, the net rotation is about 90 degrees. Okay. So, any rotation that happens in 3D essentially is rotation that is happening by an angle about a axis. That does not mean that that axis is one of the principal axes and the angle is one of the Euler angles. Here I am talking about the net rotation that is happening, the total rotation is happening about an axis, and the angle that it rotates about is the net rotation. For example, I can represent this rotation as a combination of multiple rotations, as a combination of three rotations in the three axes. The question is, how do I find the axis of rotation? Well, that is the particular vector, that is the particular line that does not change due to rotation, right. For example, if this object is undergoing that rotation, right, let us mark a point here that will undergo a change due to the rotation, but the axis, the set of all points on the axis of rotation will not undergo any change due to rotation. Okay. So, suppose R is a rotation matrix. So, I can perform an eigenvalue decomposition and represent this as Rx is lambda x. So, the characteristic equation then is R minus lambda I times x is 0. And the question is what is this x? It turns out that the rotation matrix R will have an eigenvalue 1. The eigenvector that corresponds to eigenvalue plus 1 is the axis about which the rotation is happening. We will take some simple examples and check if this is indeed true. Now, the question is, what about the angle of rotation? How much or by how much the rotation has happened? Well, that you can find by using this relationship, 1 plus 2 cos beta is trace of R. From this find the value of beta. That is not really too difficult to find. So, if you have the rotation matrix, find the trace of that matrix. The trace of that matrix is 1 plus 2 cos beta, and find the value of beta from this relationship. Okay. That is the relationship between the angle of rotation and the rotation matrix. Remember, what is this beta? Is it the rotation about the x axis or y axis or the z axis? Remember, this beta is not an Euler angle. This is not an Euler angle. This is the net angle of rotation. Okay. This is the net angle of rotation. Now, let us check if this is true for the simple case when the rotation is happening about the x axis by an angle theta. Okay. Okay. So, what would be the rotation matrix? We know what the rotation matrix is from the previous class. That would be 1 0 0 0 cos theta minus sin theta 0 sin theta cos theta. This is the rotation matrix R, right. In this case, what is the trace of this matrix? The trace of this matrix is the sum of these three elements, is it not? That is 1 plus 2 cos theta equal to the trace of the matrix R, is it not? Now, it is very clear that the rotation angle is theta. How do you know this? Just compute this and you will know that this rotation angle is theta, because you just have to take the you just have to look at the rotation matrix and it is immediately obvious that this is a rotation that is happening about the x axis and the angle of rotation is theta, right. Now, of course, this is the simple case of the rotation happening about one of the three principal axes, right. This is the case when the rotation is happening about the x axis, but the question is, what would this be when the rotation is a composite rotation? That is, the rotation has components in all the three directions, in all the or about all the three axes there is a component of rotation that has happened. Now, what is the angle of rotation? Remember, once again, this angle of rotation that we are discussing for a composite rotation matrix is the net rotation. You cannot compute the Euler angles from this. Okay. This is not an Euler angle, but the net rotation that has happened. For example, I gave the example of this phone being rotated, right. So, this is the phone and I am rotating it. Now, because the three axes have different components for this rotation or for the axis of rotation, the net rotation might be some angle, say 80 degrees or 90 degrees in this case, but the Euler angles for each of the three or the Euler angles about each of the three axes will not be that value. So, you cannot find the Euler angles by looking at the net rotation. Here what we are looking at is the net rotation and the axis of rotation. This axis of rotation may have components about the three principal axes. Something to keep in mind, that there is a fundamental difference between these axes and this angle and the Euler angle, right, and the principal axis. So, this is a simple concept that you can use to find the actual axis about which the rotation is happening and the angle of the net angle of rotation. Okay, something to remember and keep in mind. Okay. Now, let us use quaternions. Let us discuss the concepts of quaternions and how we can use quaternions to parameterize rotations. Now, this is something that we know from high school. I have an I have a complex number, say a plus ib. Now, this has a component a along the x axis and a component b along the y axis. Now, I can represent this also as a vector, for example, that vector and an angle, that rotation. It is as if I have taken this vector along the real axis and rotated it by that angle theta, right. So, let us say I know a and b, I know the values a and b. How would you find theta? From high school mathematics, I know that that is actually tan inverse of b by a, we know this. Now, let us suppose a is 0.707 and b is 0.707, then theta is 45 degrees. What is the magnitude of this? That is the square root of the sum of the squares, right? Not, this is the magnitude, that is r, right. This is also something that we know from high school math, right? Not. Now, let us suppose that I have two complex numbers a plus ib and c plus id, where a is 0.707, b is 0.707, theta is some 45 degrees, c is 0.877 and d is 0.5 and theta is some 30 degrees. So, that is for these a and b, the corresponding theta is 45 degrees, that is when a and b are 0.707, the theta is 45 degrees, and when c and d are respectively 0.877 and 0.5, theta is 30 degrees, right. Now, what is the length of these two complex numbers or these two vectors? That is actually 1, because square root of a squared plus b squared is 1 in this case. Now, let us say that I am multiplying these two complex numbers a plus ib times c plus id will give me another complex number with real part ac minus bd and an imaginary part ad plus bc. Okay. I perform this multiplication and I find this is actually, the real part is actually 0.266 and the imaginary part is actually 0.974 approximately. And the length of this multiplied complex number, the new complex number, that is the product of the two original complex numbers, is also 1. Okay. That is that number in the unit circle, that is this number on the unit circle, and you realize the theta for these two imaginary and real parts turns out to be 75 degrees. What this means is that multiplying these two complex numbers essentially implies that I am adding these two rotations one after the other. First I am doing a plus ib, then I am doing c plus id, resulting in this composite, in this rotation, that is the sum of the two individual rotations 30 degrees and 45 degrees. When you sum them, the net rotation, the total rotation would be 75 degrees. For this to happen, there is a condition, there is a precondition, that is the length should always be 1. Only when the length is 1, you can actually represent, or you can use complex numbers to represent rotations, something that we need to keep in mind. Now, let us look at how we can use the complex number representation to find relative orientation. Remember, in one of the previous videos, we looked at finding the difference or relative orientation between two joints as for example, something like R2T times R1, something like this, right, remember. Now, what is this R2 and R1? These are rotation matrices. The question is there an equivalent in the complex number space for this transpose? Right. Yes, that is there, that is the complex conjugate. Right. Now, if I have a complex number x plus iy, what is its complex conjugate? We know that that is actually x minus iy. Right. That is the complex conjugate. Now, if I am interested in finding the relative orientation between these two points, that is a plus ib and c plus id, where a and b were 0.707 and 0.707 respectively, that is what we saw in the previous slide, that is representing theta as 45 degrees, and c plus id where c is 0.877 and d is 0.5, representing theta equal to 30 degrees. Right. Now, remember both of these have length 1. Suppose I find the complex conjugate of this, right. I find the complex conjugate of c plus id and I multiply it with a plus ib. Here it shows actually as plus, that is actually a multiplication. Okay. So, this is actually c minus id times a plus ib. Okay. That will actually give you another complex number with real part ac plus bd and imaginary part bc minus ad. Remember that this is different from what we did previously, because here I am not multiplying a plus ib and c plus id, rather I am multiplying c minus id and a plus ib. Okay. When I do that, I will get this complex number, and if I find the theta as tan inverse of b by a, I will get 15 degrees. Now, what is this 15 degrees? This is the difference between the original, the first angle 45 degrees and the second angle 30 degrees. Remember, we performed this R2 transpose times R1. Now, the transpose is going to help you find the relative orientation, remember. So, if I have a plus ib times c plus id, then that is essentially similar to addition, and if I multiply the complex conjugate of c plus id with a plus ib, that is similar to subtraction. Of course, this will work only when the magnitude is 1 or when all of these numbers are on the unit circle, otherwise this will not work, but this is an interesting formulation. Now, similar to what we had a plus ib, c plus id, what is this I? What does this I represent? It just tells you that what follows this I is the imaginary part. This is a complex number with an imaginary part I, that is what it tells you, right. Now, similar to that, let us suppose I had a vector q a b c d like this, right, such that a squared plus b squared plus c squared plus d squared is 1. Remember, in the previous discussion we just said that a squared plus b squared is 1, or rather the square root of a squared plus b squared is 1, but the square root of a squared plus b squared, if it is 1, then a squared plus b squared is 1. So, right. Now, this a squared plus b squared plus c squared plus d squared is such that it represents a hypersphere in 4D space. Immediately what we realize is that 4D, that is not intuitive. That is the issue with quaternions, that the instant you say quaternions, they are not immediately intuitive. You are not having a feel for this, unlike Euler angles, for which you have a feel, you have an idea of what is going on, but in quaternions, because this is in 4D hypersphere, you do not have an idea or you do not have an intuitive understanding or feel. That does not mean that this is not as useful or as critical. This is a very useful method, but with some difficulty or with a lot of difficulty in getting an intuitive feel for this. So, all these points, remember when we represented the complex number, we said that is the number a plus ib. Now, this is on the circumference of the unit circle, right, correct. In this case, for a quaternion, this will be a plus ib plus cj plus dk. Each of this will be such that this quaternion will be a point on the surface of this 4D hypersphere. Like you are having this for the unit circle, this is what would happen when you have a 4D hypersphere, and all of these quaternions are points on the surface of this hypersphere. Okay. So, in this case, A alone is the real part and B, C, D are imaginary parts. Okay. So, this is the extension to 3D of this complex number representation. Okay. Now, in the beginning of this video, we started discussing axis and angle representation. We said that I can actually find the net rotation and the axis about which the net rotation is happening. Remember, right? This is called axis angle representation or angle axis representation, depending on how you call it. Now, let us suppose I have a quaternion q0, q1, q2, q3. I can represent this as cos of theta by 2, Vx sin theta by 2, Vy sin theta by 2 and Vz sin theta by 2. Now, in this case, it turns out the rotation, the angle of rotation is actually theta, okay, and the axis about which this rotation has happened is Vx, Vy and Vz. This is the axis, or these components in x, y and z constitute the vector about which this rotation has happened, or this is the axis about which this rotation has happened, similar to what we discussed. Now, consider these 5 sets of quaternions, 5 quaternions that are given. Find the axis about which the rotation is happening and the angle by which the rotation has happened. How do you do this? Well, we just said how to do it. We will start with the first example. What it says is cos theta by 2 is equal to 1. What does that say about theta? Well, that says that theta by 2 is cos inverse of 1, is it not? When is this happening? This is true only when theta is 0, is it not? What about V1, V2, V3? Well, V1 is 0, V2 is 0, V3 is 0. This is a rotation of 0 degrees about none of that is there is no rotation essentially about none of the 3 axes, right, because none of the 3 axes have any representation, all of them are 0, 0, zeros, right. Remember, Vx, Vy, Vz represents the axis about which the rotation happens, that is the last 3 components, right. The first one is the angle. Now, let us look at the second one, okay. 0, 1, 0, 0, okay. 0, 1, 0, 0. What does that say? Cos theta by 2 is 0. Now, that means theta by 2 is cos inverse of 0. What is that? That is pi by 2, is it not? That is pi by 2, or theta is pi. It is a rotation of 180 degrees about which axis? To find that, I can find out that Vx sin theta by 2 sin pi by 2 is equal to 1, is it not? Now, that will give me the value. What is sin pi by 2? Sin pi by 2 is 1, is it not? So, this is the axis. Also, is there any component of rotation that is happening about these axes? Probably no, because Vy sin theta is pi, pi by 2 is equal to 0, it says. That means, although sin pi by 2 is 1, Vy must be 0 for this to be 0, is it not? Likewise, Vz sin theta is pi, pi by 2 is equal to 0. How do I know? Because this is the quaternion, 0 1 0 0 is the quaternion, the third and fourth components are zeros. So, Vz sin pi by 2 is 0, but sin pi by 2 itself is 1, that means that Vz must be 0, that is what it says. Okay. So, this quaternion 0 1 0 0 is a rotation by pi radians or 180 degrees about the x axis, right. This is also called as pitch, x axis, that is 100, also called pitch, or I will write here, this is called pitch, right. Now, let us look at this case of q equal to 0.707, 0.707, 0, 0. Again, these numbers are conveniently taken so that it is not too complicated for you. The actual problems that you will come across in real life and probably in the exam need not be so simple, okay. But let us continue. So, q is 0.707, 0.707, 0, 0. Now, cos theta by 2 is 0.707. What is theta by 2, or rather theta is 2 times cos inverse of this value, is it not? We know what this value is. Cos inverse of 0.707 is actually 45 degrees, 2 times 45 degrees is actually 90 degrees, okay. Theta is the angle of rotation is 90 degrees, okay. Now, what about this? This is Vx sin theta by 2. What is theta? Theta is 90 degrees, that is sin 45, or rather pi by 4, is equal to 0.707. But we know this value is 0.707, is it not? How do you know? From high school math, right. This will give me Vx as 0.707 by sin 45, rather 1, something like that. What this means is that the rotation is purely about the x axis only, and the angle of rotation is 90 degrees, right. So, here we have taken and solved 2-3 of the quaternions. You can try on your own for these and this. So, essentially this quaternion, what does it represent? In this case, the axis angle representation represents a rotation of theta about an axis, okay, of this body, okay. Now, how do I convert this quaternion to other formats of parameterization such as rotation matrix, such as Euler angles? Why do I have to do that? Do I have to do that? The answer is yes, we have to do that. But why? Because as we just now discussed, there is no intuitive understanding of quaternions. I need to have an intuitive understanding. So, to have an intuitive understanding, I need to convert it to things that I understand well, and those are Euler angles and rotation matrices. And so, suppose I have this quaternion Q0, Q1, Q2, Q3, I can convert this into the rotation matrix using this formula, using this formulation. I am not performing the derivation showing that this is indeed true, but you can check whether this is true. This is true, okay. This is true, and then I can convert from this rotation matrix to Euler angles, okay. There is a way to convert directly from quaternions to Euler angles by using this function Euler d. Of course, I need to know the sequence of rotation. I still need to know the sequence of rotation. Suppose this was the quaternion. Remember, this is the problem that we solved in the previous slide. Suppose, is it not? That is what we solved here. That is that problem. 0.707, 0.707, right? That is what we solved. I am converting that to Euler using the Euler d formula, right. I will get the angle of rotation as 90 degrees as we found previously, right. Of course, I am taking some simple examples that are having some zeros, right. The real quaternion that you measure, or the measured quaternions from IMUs or from your electromagnetic tracking systems, will not have such simple numbers, and they will not be so intuitive. You will need to convert this to Euler angles. Of course, for this you need the MATLAB function. Of course, this is the MATLAB function. There are maybe equivalents in other packages or languages. Okay. Now, like we discussed previously, how I can find the relative orientation, we just showed an example of how we can find the relative orientation. We said that you can do by finding the complex conjugate of the second one and then multiplying it with the first complex number, something like that, right. So, suppose I have two quaternions Q1 0 20 0 for example, and another quaternion corresponding to this Euler angle and quaternion corresponding to that Euler angle, for example, and I am interested in converting, that is these two angles. I am having 60 degrees and I am having 20 degrees, and I would like to know the relative angle between these two. This is the kind of problem that we will encounter in real life. Most likely this is the problem that we are interested in solving, right. Of course, the numbers given are simple, 20 and 60. Obviously, you know that the relative angle between this, let us say this is the proximal segment and this is the more distal segment, is 40 degrees. I know this. So, I try to convert this to quaternions first, and then I multiply the two. If I simply multiply the two, it is going to add, like we did in the complex number case. If I simply multiply the two quaternions using quat multiply of these two quaternions Q1 and Q2, I am going to simply get the sum of the two angles, but I am interested in finding the relative orientation. To do that, what we said in the unit circle case is you find the complex conjugate of the quaternion and then multiply, right. If you do that, if you do the quaternion multiplication by finding the complex conjugate of one of them and then multiply it with the other, you will get the angle as 40 degrees. Of course, the order of multiplication matters, right. Also remember that the, like you have if I have a complex number x plus iy, its complex conjugate is x minus iy. Now, for the quaternion q naught, q1, q2, q3, the complex conjugate is q naught minus q1 minus q2 minus q3. Why? Because the only real part in that is q naught, q1, q2, q3 are all imaginary parts, right. So, if I use complex conjugates and multiply using quad multiply, I will find the relative orientation between two segments. Right. Now, let us suppose that I use one IMU to find one quaternion that measures the orientation of this segment, and another IMU that measures the orientation of the first segment. Both of them are outputting in quaternions. If I want to find the relative orientation, I find the complex conjugate and then multiply, I will get the relative orientation. This is that simple. Okay. So, in this video we looked at axis angle representations. We looked at how we can find the axis of rotation and angle of rotation from a rotation matrix, that is the axis about which a composite rotation happens and the angle by which this composite rotation happens. This is the net angle, right, that we looked at for the rotation matrix case. Then we introduced the idea of quaternions, gave some simple examples of complex numbers and rotations and how to find relative orientation between complex numbers, right. And then we introduced the idea of quaternions and axis angle representation for a quaternion, and then we used quaternion principles to discuss relative orientation between two segments using quaternions, right, essentially to first find the complex conjugate of the quaternion and then multiply using quad multiply, for example, in MATLAB. So, with this we come to the end of this video. Thank you very much for your attention.